Hello viewers, in today's class we are going to take up a very important problem related to differentiation under integral sign, right? So here we'll solve this integral by using the concept of differentiation under integral sign. So let us start. So here we have the integral 0 to pi log of 1 plus alpha cos x over cos x dx, right? And the condition is the absolute value of alpha is less than 1, or in other words we can say that alpha is greater than minus 1 and less than alpha is greater than minus 1 and less than 1, right? Okay, so now here we see that alpha is known as a parameter, right? So alpha is a parameter, and here we'll consider this expression as a function of alpha, right? So let us take this integral I. Here if we take it as I, then I can be considered as a function of alpha, and this is from 0 to pi log 1 plus alpha cos x divided by cos x dx. Now we are considering this integral as a function of alpha. So let us now differentiate this expression partially with respect to alpha, and let us see what we get. So here we'll write del I alpha of del alpha is equal to del over del alpha of 0 to pi log 1 plus alpha cos x divided by cos x dx, right? So here we'll differentiate this integral with respect to alpha, and here we see that only this term, that is a log of 1 plus alpha cos x, contain alpha, right? So we have del I alpha over del alpha is equal to 0 to pi, and taking this partial derivative inside the integral and differentiating this expression, right? So this cos x in the denominator, it remains as such, and the derivative of log of 1 plus alpha cos x is 1 over 1 plus alpha cos x, and then by chain rule 1 plus alpha cos x, the derivative of 1 plus alpha cos x is simply cos x, right? And here we'll have dx. So here we have made use of the formula for the derivative of log of x, that is 1 over x, right? So here cos x and cos x get cancelled, and we have del I alpha over del alpha is equal to 0 to pi integral of 0 to pi, then we have dx over 1 plus alpha cos x, right? So let us take this as integral 1, and let us take it as integral number 2. Now here in order to integrate this function, let us apply the formula for cos x in terms of tan of x by 2. So cos x can be written as 1 minus tan square x over 2, divided by 1 plus 10 square x over 2, right? So we'll make use of this formula, right? And let us substitute this expression over here. So we have the integral from 0 to pi dx over 1 plus alpha times 1 minus 10 square x over 2 divided by 1 plus 10 square x over 2, right? Okay, now let us integrate this expression with the help of substitution method, and let us put say y is equal to 10x over 2, right? So we'll make this substitution here. So when y is equal to 10x by 2, then dy over dx is equal to half sec square x over 2, and this can further be written as 1 over 2 1 plus 10 square x over 2 by using the identity 1 plus 10 square theta is equal to sec square theta, and this can be written as half 1 plus y square, right? So we have dy over dx is equal to half of 1 plus y square. So it means dx is equal to 2 dy over 1 plus y square, right? Okay, so now we can substitute or we can change this integral from the variable x to variable y, but doing so let us change the limits, right? So when x is equal to 0, because here we have x is equal to 0, so when x is 0, the value of y is tan 0 over 2, that is tan 0, which is equal to 0, right? Similarly, when x is equal to pi, the value of y is tan pi by 2, and tan pi by 2 is infinity. So we have the limits from 0 to pi when x is the variable, and when y is the variable, then the limits are from 0 to infinity, right? So let us change this integral. So now we can write, so del I alpha over del alpha is equal to the integral from 0 to infinity, and for dx we have 2 dy over 1 plus y square divided by 1 plus alpha times 1 minus y square over 1 plus y square, right? So here we have this integral, right? Now let us simplify this expression. So we have the integral from 0 to infinity. Here we have 2 dy over 1 plus y square divided by here taking the LCM, so we have 1 plus y square plus alpha times 1 minus y square, and divided by 1 plus y square, right? Now this term and this term get cancelled, so we have the integral from 0 to infinity 2 dy over 1 plus y square plus alpha minus alpha y square, right? Now let us simplify the denominator. So we have the integral from 0 to infinity. Here we have dy, and we can write 1 minus alpha y square plus 1 plus alpha, right? So now taking 1 plus 1 minus alpha common from the denominator, so we can write this expression as del I alpha over del alpha is equal to 2 over 1 minus alpha, and here we have 0 to infinity, and here we have dy over y square plus 1 plus alpha over 1 minus alpha, right? Okay, so now let us write this expression as square root of 1 plus alpha over 1 minus alpha square, right? So we can write here 2 over 1 minus alpha, then we have the integral from 0 to infinity dy over y square plus square root of 1 plus alpha over 1 minus alpha square, right? Okay, so now this integral is of the form dx over x square plus a square, and here for x we have y, and for a we have this term, right? For a we have square root of 1 plus alpha over 1 minus alpha, and the integral of this expression is 1 over a tan inverse x over a, right? Okay, so now applying this rule to evaluate this integral, so we have del I alpha over del alpha is equal to 2 over 1 minus alpha, then we have 1 over a, for a we have this term square root of 1 plus alpha over 1 minus alpha, and then we have tan inverse of x. For x we have y, so y over square root of 1 plus alpha over 1 minus alpha, and here we have the limits from 0 to infinity, right? So now we can write this expression as del I over del alpha is equal to 2 over 1 minus alpha, and taking this term outside the bracket and taking the reciprocal here, so we can write square root of 1 minus alpha over 1 plus alpha, and here we have tan inverse of y times square root of 1 minus alpha over 1 plus alpha, and the limits are from 0 to infinity, right? So now this expression can be written as 2 over 1 minus alpha times 1 plus alpha, and here we have tan inverse of, first we will substitute infinity here, so we have for y we have substituted infinity, then we have 0 for y, so we have tan inverse 0, right? So now this expression becomes 2 over square root of 1 minus alpha square, and here we have tan inverse of infinity, which is pi over 2 minus 0, right? So now this is 2 over square root of 1 minus alpha square, and here we have pi over 2, 2 and 2 get cancelled, so we are left with pi over square root of 1 minus alpha square, right? Okay, so viewers, we have this the original integral, and here we have obtained this expression, right? That is del I over del alpha is equal to pi over square root of 1 minus alpha square. So we have here obtained a differential equation in I, right? A differential equation in I alpha. So now this is a first order variable separable differential equation. So we can solve this differential equation by separating the variables. So we can write here di alpha and taking this d alpha to this side, so we have pi over square root of 1 minus alpha square d alpha, right? Now integrating both sides, so here we have di, so here we are using I for I of alpha, so we have di, integral of di, and here we have integral of pi over square root of 1 minus alpha square d alpha, right? And plus c, so c is the constant of integration. So here we have I, and taking this pi outside the integral sign, so we have d alpha over square root of 1 minus alpha square plus c. Now viewers, using the famous integral, that is dx over square root of 1 minus x square, is nothing but sine inverse of x, right? Okay, so now using this result over here, we have alpha for x, so we can write I of alpha is equal to pi times sine inverse x, or we can write sine inverse of alpha, right? And plus c. Let us take this as equation number 3. Now here our aim is to find out this constant of integration, and for this we'll first make use of this integral. So in 1, if we put alpha is equal to 0, then what will happen? Then we'll have I of 0, right? Here we are substituting alpha is equal to 0, so I of 0 is 0, right? Because this term, that is log of 1 plus 0 times cos x, it becomes log of 1, that is 0. Clear? Okay, so I of 0 is equal to 0, so we are going to utilize this condition to determine the value of c. So here we will substitute alpha is equal to 0, so we have I of 0 is equal to pi sine inverse 0 plus c, and for I of 0 we have 0 here, and here we have pi times 0, because sine inverse 0 is equal to 0 plus c, so we have 0 is equal to 0 plus c, that is equal to c is equal to 0, right? Now substituting this value of c in equation number 3, we'll get I of alpha is equal to pi sine inverse alpha, right? And what is I of alpha? I of alpha is our original integral, right? So the value of the original integral is equal to pi sine inverse alpha.